Hello everyone, how are you? Okay, let's get started. All right, do I have sound? I have sound. Okay, let's go ahead. So as a reminder, there's going to be an exam in the class on Friday, and I also posted onto the Canvas that if anybody has a need to take the exam in the alternate time slot, which is at 9 o'clock p.m. Eastern Time on Friday, please send me a message before 2 p.m. Eastern Time on Friday. But as I said, the exams will be totally different. I have to still make the problems, so I don't know what the problems will be yet, but I promise you they'll be interesting. Okay, so let's continue on and finish up maybe the last topic of this particular section of the course. And actually the stuff we talk about today could also be on the exam as well. So for today's topic, actually, I'm not sure if some of you may have seen this one before if you were in one of my other classes, or if you saw it online on some talk I gave. If you have seen this before, please don't give it away, but it's really cool. So I'm going to talk about binomial coefficients, but now let's talk about some number theoretic properties of binomial coefficients. Specifically, what if I'm curious about what is the last digit of 62 choose 22. Quick thing I want to double check. Can I have a quick raise of hands I want to double check, is this something I talked about this year in the Putnam class? Because I talk about it every 4 years in the Putnam class, and I forgot which year this is. I see a wave. I'm guessing the wave means hello. I think it means no. Then that's good. Okay, then this is neat for people. If you haven't seen this before, you get to play. If you have seen this before, don't give it away. So, okay, how do you go about figuring out the last digit of a choose? 62 choose 22. Any ideas? Feel free to raise your hand. Somebody said that this is on a practice exam. Yes, now you're seeing that there's something related to a practice exam. So how do I do this? Well, I mean, I'm just looking for any ideas. You don't have to have a solution, by the way. Just some ideas. Jack.
I think the last digit of the number is it's remainder when divided by 10. And I know there's math about remainders, basically, right? Division.
Okay. We're doing something with remainders. Divide by 10. Good idea. Any other ideas how we might try to approach a question like this? Again, I'm not expecting answers. This is hard. I'm just looking for any ideas. Venkatesh.
I guess so. If you expand it, right, like on the top, you have 62 factorial over 22 factorial over 40 factorial.
Okay, that's a formula. Now what?
And then like you take out the 40 factorial on the top as well and on the bottom, so it's like 62 times 61 all the way to 41.
Okay.
And then you're dividing by 22 factorial still. So on the top you can see that there's 3 multiples of 10, or no, 2, 60 and 50, right? And on the bottom there's also 2 multiples of 10. So you can like cancel those out. So I guess I was thinking it might have been 0, but maybe it's 0.
This is a good idea, okay? I'm writing all of this stuff down. This is all kind of relevant. What you're saying is like, how do you make a 0? You know, you have tens. Let's like take out the factors of 10. That's a pretty good idea. And this is, I'm putting this down because it's relevant to how we solve the question. Although I will say, I'm glad you didn't suggest the first thing, which was, you know, if I want to know the last digit, all you do is you multiply the top together, find the last digit, multiply all the bottom together, find the last digit, and divide those by each other.
Yeah, like that doesn't work.
Why doesn't that work in this in particular? What's the last digit if I multiply the top? 0, and the bottom is 0, and now you got nothing. And in general, you can't do that by dividing by, you can't divide that way. With these modular arithmetic, you can multiply and you can add and you can subtract. Dividing is tough if you're not using a prime. 10 is not prime, so that's too bad. What else can we do? Sydney.
It's definitely not a solution, but like going off the log 10 thing, maybe we can replace everything in the top with like its equivalent log 10 and on the bottom too.
Okay, so now there are some ideas, right? Here's another idea. If you replace everything with its, I'm going to call it residue. You said equivalent, but that's what typically we use. Mod 10, I'll say if you did that, you get 2, 1, 0. You get a bunch of zeros, which is like that's a little bit difficult. I've got all these zeros, but it's an idea. Advait, what do you think?
What if you first cancel out all the powers of 10 in the top and bottom?
Okay, so we want to do like a cancel.
Modding you want.
Oh, so you're like, let's get rid of these like 10s. The zeros are annoying, right? And so since I can cancel out the zeros, yeah, okay, let's do that. Let's see what happens with combining Sydney's idea together with this like observation up there, and Advait says cancel them out first. So if you did that, let's combine. So what we really have is we have something like 62 times 61 times, now the 60 we already canceled out a 10, right? Times 59 times 58 times ... times 51 times, instead of 50, I just write a 5, okay? Times 49 times all the way to 41 divided by, on the bottom I have 22 times 21 times, instead of a 20, it's a 2, times 19 times 18 times all the way to 11, but instead of 10, it's just a 1. The 10's gone. 9 all the way down to 1. And then the idea was like, what if we replace all of them with like the last digit instead? So that's an interesting idea. What happens? If you replace all of these by the last digits and then multiply, what's the last digit on the top?
Oh, hold on. I meant you gotta cancel out all the powers of 10, meaning like 2s and 5s.
Ah, 2s and 5s also. Okay, so that's what I want to get here, right? It's because if I try to multiply all this out, I have like even numbers, and there's this 5 sitting there, which is a problem, because you multiply and again it ends with a 0. So what I'm going to say, we could do that. That's going to be a lot of like writing stuff, but I'm going to say that the takeaway message is you need to do something with the factors of 2 and 5. So that's a hint. I want to move towards another way to solve this problem where I don't have to write out as many things. And it's actually going to give us another combinatorial thing we can use, which is we need to do something about 2s and 5s. Oh, Isain, what do you want to do?
I was thinking since we cancel like 10 to like 5, then maybe we can like, is there a way to put like prime factorization?
Ah.
Maybe like help us in testing like more than
Good idea. Let's do something with prime factorization, and let me use that to give a hint. There's something that you may have learned in concepts of math, where it's like, if I want to know what a number is when I divide by 10, what the remainder is, if I know the remainder after dividing by 5 and by 2, I get some information. Is that something people saw in concepts, or is that not covered in concepts? I'm actually curious.
I think this term, yeah, they spent like, they didn't really use that part of it at all, but yeah, it's the Chinese remainder.
There's some Chinese remainder theorem about like, since 10 is not prime, but 2 and 5 are, you can get a lot of mileage out of those. So we won't need the whole Chinese remainder theorem here. Let's just do it simpler. First of all, let's think about what is the remainder when I divide by 5. Let's start with that. That's a nice simple thing. So here let's go to another question. What is the remainder when you divide by 5? Now, how might we try to do that? If I want to know, I have like all of this stuff. I've got 62 factorial over 22 factorial, 40 factorial. I want to know something about what happens when I divide by 5. Venkatesh.
Count all of the powers of 5 on the top and on the bottom.
Okay, so I think what you're getting at is there's actually a very famous kind of question in math contest world called, you have 99 factorial, how many zeros does it end in? I'm not sure how many people saw these kinds of problems. These are the ones that are usually put like on a projector screen at the last round of a middle school math competition, and some kid gets it like super fast and the parents are all like, wow, how'd you do that? But there's a nice trick, all right? So let's talk about that one first. So there's a general trick that if you have a factorial, to find out what is the biggest power of 5 in that factorial. By the way, that's the same as the answer to the how many zeros does it end with. Does that sort of make sense? If I have a factorial, and you think about how many factors of 5 it has, and how many factors of 2 it has, of course you'll have more 2's. It's easier to get 2's. So it's almost like some kind of a chemistry reaction. Your limiting reactant is the 5's, okay? But what we'll do here is let's go with a simpler question first. What is the number of 5s in, oh, let's just call it, what was it, 62 factorial. Oh no, I want a punctuation mark. All right, here, this is a punctuation mark. I just don't want to be like that. That's an exclamation. Okay, so what's the number of 5s in 62 factorial? Does anyone know this? And actually, was this covered in some other class here, or is this just that people know it? Maybe. Someone raise hand. Isin. Is that, no, Thomas.
12.
Why?
Well, because there's 6 5s and 6 10s.
Oh, okay. So you're like, there's 6 5s and there's 6 10s. 6, I think what you mean is there's 6 numbers of the form x5. Is that okay? And there's 6 x zeros. Is that what you mean?
Yeah.
X is not times, x is like some random digit. Okay? So that would give you 12. Because it's like, actually, if you think about it, I also know something else there. It's like, if I took 62 and divided by 5, that's equal to 12 point something. So that's why I would have 12 multiples of 5 up there. So it looks like there are 12 factors of 5 in 62 factorial. But there's something a little bit annoying about this question. There's a few more. Dhruva.
I think 25 and 50 also have an additional factor of 5.
But 25 and 50 give extra 5 each. So actually this gives you 14. And the way to think of this is that, the way I often explain it real quick is I say, look, what are these factors of 5 you're talking about? Well, those happen to be 5, 10, 15, 20, 25, 30, 35. I'm writing it all down on purpose. 40, 45, 50, 55, 60. These are all of those powers. And now I'm going to draw a little diagram where I put 1 dot for how many powers of 5 there are. And the 25 gets 2 dots because there are 2 powers of 5. 35, 40, 45. The 50 gets 2 dots again. And the 55 and the 60 get 1 dot each. Does my dot diagram make sense? This is like how many 5s? That's what this is. Green is how many 5s. But now the easiest way to think of how you get this 12 plus 2 is that actually to get the 12, you first do 62 divided by 5, and then you round down. That's this first column. Braden, did you want to say something?
That was on the last comment, but I can finish this out.
Go for it.
Yeah, and so we count all of the 12 multiples of 5 once by dividing by 5 and taking the 4. And then we can divide by 25 and take the 4 of that to count all the numbers which have 2 factors of 5.
Yep. That's the second column. I'm just going to circle those. So the way to think of this is that if I want to know how many dots I've got, the first column is just divide by 5, the second column is divide by 25, and if I just take the first column plus the second column, that's all the dots. All right, so the formula for this happens to be the 62 divided by 5 plus 62 divided by 25, and that was equal to 12 plus 2, which is 14. Okay? Let's carry on. Let's go to the next thing. The next thing was, we have, the whole thing is 62 choose 22. So I also need to worry about 22 factorial and 40 factorial. So let's quickly do the same thing. How many, let me rewrite what we had so far. How many 5s in 62 factorial? That was 14. Okay. Now we have another question, which is asking the same thing for 22 factorial. What's this now? We can do this one much faster. What is it for 22 factorial? Anyone want to tell me the answer? I see an answer. 4. 4. Because in this case, I just do 22 divided by 5, round down, and that's it. Because there's no point going to divide by 25. You're not even getting to 25. Okay? Let's do the last question around the 5s. How many 5s are in 40 factorial? What's this one? I see Venkatesh has said 9. And that's because you take the 40 divided by 5, And now we also need to do 40 divided by 25 because we do have some multiples of 25. And so that's equal to 8 plus 1 equals 9. Okay. Question, Chris.
Does this extend to every power 5?
Yes, it does. Yes, it does. Because actually, let's go back to that picture, okay? So, for example, imagine I kept going and going and going until like 200 or something. Notice that at some point, I will have 125s, and that will give me 3 across, right? So the way that this formula generalizes is it's the number over 5, round down, plus the number over 25, round down, plus the number over 125, round down, and plus forever. And by the way, over here, you could actually also have thought of this as plus 62 over 125 round down. But what's that anyway? 0. Won't make a difference. So it's all consistent. In general, the number divided by a power of 5 tells you how many dots are in that column. Okay? We will actually see that when we start worrying about the powers of 2. It's a lot easier to run into 2 to the power 3. That's just 8. And 2 to the power 4. That's just 16. We're going to get quite far. Okay. What's the punchline from this? So now I know how many 5s there are in 62 factorial, in 22 factorial, and 40 factorial. So then the question is like what's the 5-ness? That's not really a word, but I think you know what I mean. What's the 5-ness of 62 factorial over 22 factorial, 40 factorial? Is there any way to tell me something about like 5-ishness of this? We know that there's 14 5s in 62 factorial, and 4 5s in 22 factorial, and 9 5s in 40 factorial. Advait.
Well, you can just add the 5-ness of the 62 and subtract the 5-ness of the 22 and 40 to get that there's 1 power of 5 remaining at the end of the day.
Okay, so it means if you go and cancel and cancel and cancel, by the time when you're all done canceling, it's like there's still a 5 surviving on top. Is that okay? That's the important thing here. So it's like the answer to this is since you have 14 5s on top and 4 plus 9 equals 13 on the bottom, after canceling, still have 5 on top. So that means that, well, actually, there's no more on top. You still have like 5. Because there's no more top and bottom. Does that make sense? When you're done canceling, you just got an integer. You still have 5 as a factor of the integer. By the way, I just made something pretty awesome, a pretty awesome claim. It is that, did you know that if you took 62 factorial divided by 22 factorial, 40 factorial, it'll all cancel? It doesn't deserve to. Like if you take some random factorials and multiply and divide, like it's a miracle that they cancel. But we know they cancel because of counting in 2 ways. We know that that's just the formula for how many ways there are to choose something. And the number of ways to choose something, well, that's going to be a whole number. So we know that it's going to work. And we know that when we're all done canceling, there's a 5 left over. What does that mean about the last digit of this answer? We've now learned something quite powerful about this. I now know what's the last digit of this answer. Aha, I see a lot of people saying it's 0 or 5, right? Because it's a multiple of 5. So now I know the answer to the question is either 0 or 5. So the last digit is 0 or 5. How could you possibly distinguish between the 0 and the 5? Anyone have an idea? Flip a coin. That's one way. But there's another way, mod 2, advaits, right? Because look, if I can figure out whether the answer is odd or even, well, it's either going to be odd or even. Does that make sense? It's like, this is very satisfying. We've gotten it down to just, 2 possibilities, and it's just odd or even. That means, so, if we could just figure out odd or even, then you're done. You can tell apart which of 0 and 5. Now we need to do mod 2. Can somebody tell me what I should do computationally to go and figure this out mod 2? It's an extension of the stuff that we've just done. Count the 2s, Cindy, thanks. Count the 2s. We just counted 5s, right? So if we counted 5s, we found out there was a leftover 5 on top. Therefore, it was a multiple of 5. Therefore, it was 0 or 5 ending. Now let's just count the 2s and see whether or not there's like leftover 2s or not. So let's go over here. Question. How many 2s? How many 2s are in the 62 factorial? Well, now we have to do more arithmetic, which is not fun. But if you can see, this is why Chris's question was good. You're just going to take 62 divided by 2, round down. And then you're going to do 62 divided by 4, round down. And then divide by 8, round down. And you keep going and going and going all the way to divide by 32 and round down. 62 over 4, round down, plus 62 over 8, round down, plus 62 over 16, round down, plus 62 over 32, round down. Okay? And this is for the same reason that the counting 5s was okay. Well, let's do it. What is this? 62 divided by 2 is 31. 62 divided by 4, 4 times 15 is 60. And it's like 15 and a half is the answer. 62 divided by 8. 8 times 7 is 56. Oh, I see a question. Oh, you already got something. Raise hand. Braden, did you just say Braden? Yeah, Braden, what's up?
Another thing that we can do is we can just take the half, like whenever you go from 15 to the next one, we can just take half of that and then you can take the 4 of it.
Yes. So the important thing is I was showing you the slow way, which is like, oh my gosh, what is 62 divided by 8 round down? 8 times 7 is 56. Okay, it's that one. But the easier way is once you get the first one, to get the next one, you just take half of the first one and round down if you need to. That is actually true. And the reason why that's true is if you look at the picture, this kind of a picture we had here, this was with 5s. You could imagine the same thing with 2s. But when I want to go from one column to the next column, what happens with the 5s is you grab every 5th one. That's why with the 5s, the next number is just always the previous number divided by 5, rounding down if you need to. Because if you went to a column and you went to the next column, you take every 5th one in the previous column. And the round down is because you only take the 5th one. And if you only got partial of the way along there, no partial credit. It's all or nothing. Now, with the 2s, it would just be that every column to the next column is every other one you pick. So that's why to go from one number to the next number on the 2s, you just divide by 2. Okay, let's continue. So in that case, now we can use this trick. 7 divided by 2 is 3 plus the remainder, so just round down to 3. And then 3 divided by 2 rounds down to 1. Much easier. Okay, and we're going to use this to simplify our work. Now we have to add these. Advid, you said it's 57. Do we believe him? 7 plus 3 is 10. 31 and 15 makes 46. 56. 57. Okay, I believe you. 57. There's 57. Next, let's do the same thing with how many 2s are in 40 factorial. Well, now we're going to do it much faster. Because now we know this trick. You take 40 divided by 2, which is 20. I'm just going to write down the thing with Braden's idea. It's like you take 40 divided by 2, round down. That's 20. Then you take 20 divided by 2. That's just 10. No need to round down. Plus 10. 10 divided by 2, still nice, 5. 5 divided by 2 rounds down to 2. 2 divided by 2 is 1. Is this okay? Ah, I see that somebody said something. Alfonso. Oh, interesting. 62 minus 40 is 22. So each even number will have 11 less 2s, right? I'm not sure I completely understand your point. The reason I'm not completely sure I understand what you're suggesting is because the issue is, like, if a number is divisible by 16 or not, if I add like 22 to it, or if I add 40 to it, it won't still be divisible by 16. So the thing about this divisibility is a little bit more tricky than that. So I don't think it's that easy to be able to just shift it across by 40. So let's just do this slowly first, because let's see what kind of answer we get here. This I can add. 30, 35, 37, 38. Maybe somebody already typed 38. Okay, let's finish the last one. How many 2's in 22 factorial? Well, that's just 22 divided by 2, which is 10. No, which is 11. Half of that is 5, with a little bit of remainder. And we already know what happens when you see a 5, because we saw a 5 earlier. So that's 5, 2, and 1. Because if I got a 5 earlier and it finishes with 5, 2, and 1 as I divide by 2 and round down, I'll see the same thing again. What's that? 11, 16, 18, 19, 19, 19. Okay, so what? Can anyone tell me what's the 2-ness? What's the 2-ness of, that was ness of 62 factorial over 22 factorial 40 factorial? Ah, this is interesting. Isane, what do you see?
So it's actually 0, meaning that like the ending digits won't be the one finished by 0, but moves to like the 5. Let's cancel out our confusion that we had before with 5.
Aha, so all the 2's cancel. So the answer is not a multiple of 2. That's powerful. The answer is not a multiple of 2. I did see that there was a comment I want to hit. Ling Ray, would you like to tell me what you mean? If they add to this, oh, I understand. You're saying this thing. They both add to 57. Yes. So we found out that they have the same number of 2's. So there's like no 2's left over. So what's the answer to the whole problem? Because now I know that there's not a multiple of 2. What's the answer? Braden, yes. 5. It's because it's odd. This means that it's odd. And we now know that the choices were 0 and 5, right? 0 and 5. And so it has to be 5. We're done. All this hard work. So 0 versus 5, it's not the 0. And the answer is it's 5. All this hard work managed to solve this question. Well, I'm going to tell you, it turns out that there's a much easier way to solve this problem. I wanted to do all of this so that we can, appreciate the shortcut. But there's a shortcut. The shortcut's actually very simple. We're doing 62, choose 22, right? We care about what this is, mod 10. All right? And this is the real reason that you write the chooses this way. This is 62, choose 22. You just do that. Okay? And so, congruent mod 10, 6 choose 2 is 6 times 5 over 2, that's 15. 2 choose 2 is 1, 5. Done! If you believe that, you should also believe this. 16 divided by 64 equals, cancel, 1/4. It's true. It's true. Okay, so something's going on here. So there's actually a theorem. So first of all, no. Be very careful. This is not the case. Be careful. Don't try this at home. Don't try at home. There's something else that's going on. The reason is only because primes. It's because 10 is not prime. Since 10 is not prime. And the significance of the 10 is that that's the 10. If we were doing this modulo a prime, actually this would work. And so that's what I want to prove next. It's a miraculous theorem that I did not believe the first time someone told me that it was possible. But it's called Lucas's theorem. And it's true that you can do this crazy looking thing if you're doing things modulo primes. Okay? So let me put a Lucas's theorem. This is Lucas's theorem. Lucas's theorem, I'm going to write it for a very specific example. And I will say it extends for all ways of doing this for any prime. Okay, so the Lucas's theorem says, let me do for one example, and then we'll understand what that means. I'm not writing a theorem statement, I'm just writing an example. The example is, if I want to know what is 17, choose 7, mod 3, I know that in concepts you might have written the mod 3 off onto the right, but I think people understand all I'm doing here is put this thing here. Oh, question. Oh no, not the number 7. Oh yeah, the number 7 is back. I like 7. Okay, so this thing, mod 3, what you do is we care about things like modulo 3. That's like the last digit in base 3, okay? And modulo 3 is the same as the last digit in base 3. So let's go and convert 17 and 7 into base 3. So what you do is you go and convert 17 in base 3. Can anyone tell me what is 17 in base 3? Got some 9s, got some 3s, and got some 1s. 1, 2, 2, thank you. 1, 2, 2 in base 3. All right? And the 7 in base 3, what's 7 in base 3? No 9s now. 2, 1, I think. Yeah, 2, 1. So 7 in base 3 is 2, 1. But I'll even put an O in front just for fun. O, 2, 1. Because that's 2 times 3 plus a 1. And what you do here is you do this ridiculous thing. 1, 2, 2, 0, 2, 1. Choose. It just feels very satisfying to do that because that should not be allowed. But you just like choose this way. And what is this? Well, it turns out that this is 1 choose 0. There's one way to choose nothing from 1. 2 choose 2. One way to choose 2 things from 2. And 2 choose 1 is just 2. Bam! Done. 17 choose 7 is 3 modulo 2. That is true. So Lucas's theorem, what I'm going to say is mod...
2 modulo 3.
Oh no, what did you say?
You mean 2 modulo 3?
I do mean 2 modulo 3. What did I say?
3 modulo 2.
Oops, that was backwards. Okay, thank you, Brayden. 2 modulo 3, okay? So Lucas's theorem is mod a prime, you can do this. And what is this? This is, over here, you write the top and the bottom in base P. Oh, I guess the prime is called P. Here, this 3, that's the prime P. All right? And this is a super overpowered theorem. It's actually really neat that you can do this. In fact, it lets you very quickly get some of these facts that we got with the mod 5 and the mod 2. We could, if you want to have some practice, you can just go and try to do the 62 choose 22, write it in base 5, write it in base 2, and we'd be able to find out what is the remainder when I divide by 5 and what's the remainder when I divide by 2. There's a reason I just said that. It's because I cooked 62 and 22 on purpose. First of all, I cooked them on purpose so that the weird coincidence would work. It doesn't always work. But the second thing is I cooked them so that it would actually give you that it was like 0 mod 5. Because if you think about what we did in the previous approach, if we had found out it's not a multiple of 5, we'd not be in good shape. Because if all I knew is it's not a multiple of 5, now the last digit, I have 8 choices. How do you tell apart 8 choices just with the evenness or the oddness? It's not powerful enough. So what we're doing here is much, much better. Question, Andrew. How do people even think to check if something... Yeah, I don't know how you think of checking that something like this is true. But it's cool. Let's go prove it now. I just want to make sure you get to see the proof of this, like, before we finish. So, okay. Lucas's theorem, ridiculously cool. Advait.
So, like for a proof, can you do it by induction based on like how many digits this thing has?
You could, but I want to do something else. I have a very visual proof. So let me go with a different visual proof instead, okay? So here's the proof of the Lucas's theorem. Proof, but I'll do the proof for this 17 choose 7 mod 3, okay? And if you had it for like a different P, you could do it in a different way, all right? So what you do is, what is 17 choose 7 anyway? Well, 17 choose 7 is just the number of pictures, okay? 17 choose 7 is equal to the number of pictures like this. What I'll do is I will draw, 17 dots. Here, 17 dots. Come on, 17. Where do I put the last one? In the middle. Okay? And I go and choose 7. What's 7? That looks like 7. Yeah, 7 dots. That's one of the pictures. And I do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Stick the 1 in the middle. Oh, choose 7. 1, 2, 3. What should I do now? 4. Let's just be weird. 4. Let's pick 7 more. Oh, 7. Okay, there. These 3. Connect it all up. I am trying to emphasize how ridiculous of an idea this is. This is stupid. Like how in the world can you draw all of these pictures? And there's like all these different ways to pick 7. You're not making any progress. And the real reason it's stupid is because it's the wrong way of arranging the dots. Instead, it'll be the number of pictures of a slightly different form. I don't want to put the 17 dots like this. Okay? New screen. 17, choose 7. The pictures we're going to do, let's remember, we have some like base stuff, right? 17 is equal to 1, 2, 2 in base 3. That's 9 plus 3 plus 3 plus 1 plus 1. So now I'm going to draw the pictures slightly differently. Here, I'm going to draw a circle of 9 things. It's like a wheel. 9 things. 1, 2, 3, 4, 5, 6, 7, 8, 9. There's 9 things in that wheel. Then I'm going to draw a wheel of 3 things, 2 wheels of 3 things. Those look like triangles. These are 2 wheels of 3 things. And 2 wheels of 1 thing. That's 17 dots. And let's just go and pick out 7 of them. Here's 1. That's 3. Oh, maybe pick all 3 of these. That's 6. Here, 7. I drew 1 picture. Next. So that's one of the pictures. Let's draw another picture right under it. 1, 2, let's use a different color for the dots so that it's clear it's a different picture. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3. 1, 2, 3. 1 and 1. Let's make this dot bigger. Okay. Now I'm going to go and pick, 7 things. Here, let's grab these 3. Let's grab these 3. Let's grab this 1. Okay. I'm going to draw 4 of these pictures because I want to make some comparisons. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the 2 triangles the 2 wheels of 3 things. The wheel of 1 thing and the wheel of 1 thing. This time I'll pick 3 like this. Here we go. I'm actually being very careful how I'm picking this, and you'll find out why soon. Let me take this, and let me take this guy. And I'm going to draw the last one. The last one is going to be here. 1, 2, 3, 4, 5, 6, 7, 8, 9. A wheel of 3 things. A wheel of 3 things. A wheel of 1 thing, and a wheel of 1 thing. And this time I'm just going to pick like 4 from the first guy, 1 from the second guy. How do you add to 7? Yeah, let's do this. I think that's 7 things. All right, I drew these 4 pictures. I claim that in these 4 pictures, some of them are kind of similar to each other, and some get more different. Can anyone give me some sense of like similarity-ness and differentness of these pictures? I very intentionally drew these. And there's like a spectrum of similarness that I just laid out. Braden.
What would we say the top 2 pictures that we've drawn? They're kind of like rotations of each other.
Ah, I called them wheels. Yes. These are like rotations of each other. And this guy, it has the right not the right number. It has the same number in each wheel as the top ones, but it's not a rotation. Does that make sense? And then this thing down here is like, well, it's totally not a rotation because there's 4 things in there. So what I'm going to say is that the top ones, these are rotations. Oops. These are rotations. Because these are wheels. You can turn the wheels. And these are not, okay? So what I'm going to do is I said 17 choose 7 is draw all of these pictures, count them all up, and that's 17 choose 7. Well, why did I do this? I did this because here's a big lump, all of these rotations. Actually, can anyone tell me how many things are in this lump? Let's look at this lump. There's two things here, but like suppose I drew all of them, okay? Draw all the rotations you've got. How many different pictures would be in the same lump as these two? How would I even figure that out? Thomas.
I was thinking 9, but are there actually only 3?
Why do you say so?
Well, I was thinking it like you just choose like where you start your like lump of 3, but you know there are going to be 3 of them that are indistinguishable.
Okay. So the point is like, look, I drew this in a very annoying way. It's like 1, 2, 3, but they're like spaced out by every 3. So what you're noticing is that this wheel, if I turn it, I only have 3 different ways I can turn it that look different. Is that what you mean?
Yeah.
Okay, so it's actually 3 ways to turn the first wheel times 1 way to turn the second wheel times 3 ways to turn the third wheel times 1 way to turn the fourth wheel times 1 way to turn the fifth wheel. Is everyone okay with the way I did this multiplication? These are all different wheels. I want to know how many, it's like a combination lock. I can have 3 choices for the first guy. The second guy, doesn't matter how you turn it, it's going to look the same. All right, so the answer is 9. Why is this so exciting? What I care about is what is the answer modulo 3. Why is it so exciting to find out that this lump has 9 things if what I care about is the answer modulo 3? It's gone. Yes, it's gone. It's like if I care about what the answer is modulo 3, forget that this guy even exists. It's not helping. Does that make sense? I care about my answer modulo 3. Just get rid of all these guys. The proof is secretly abstract algebra. Yeah, this proof is actually pretty deep, but I can explain it in a way that like high school students can understand, even middle school students. It's like this guy is just like, if I care about the answer modulo 3, this does not change the answer. So get rid of it. Technically, we can say this is congruent to 0 mod 3. So that's what lets you forget about it. Okay, well, we got another lump. Here, this lump. How many are in this lump? What's this? It's a little bit different now. How many are in this lump? Can someone tell me? It's another big multiplication. Yes, Braden, thank you. So this time the first guy has 9 rotations. Is that clear? Because it's like, the previous one was funny. The previous one kind of repeated. That's why it only had 3. But the second one has got 9. All right, size is 9 times. Now the wheel, which is all full, is times 1. The wheel, which has 1 thing picked, there's 3 ways to turn it. And then the empty wheels, and the empty wheels, nothing can happen. That's also 0 modulo 3. Hooray! So that doesn't matter either. Hang on a second. How about the last one? The same thing, okay? The last one's the same thing. This guy also, also 0 mod 3. So the answer is just 0. The answer is 0. Every lump is 0. Well, that can't be. Lucas's theorem wasn't that it's always 0. So how is it not 0? Now we just have to answer the question. Well, I've got all these lumps, right? If I care about what the answer is modulo 3, it looks like for most of the lumps, I don't care about them. Is there any lump in the world that I could care about? Ben.
Yeah, so if you choose any of the middle lumps with 3 in them, your final answer will always be multiplied by 3. So it will always be 0 mod 3. So you can't choose any of the middle lumps.
Okay, so
Sorry, not the lumps, the middle like 2 sets of 3.
Okay, I like how we're trying to dive in on this. You're like, how can I avoid having a multiple of 3? Look, everything I'm multiplying together, somehow these are all like 3s and powers of 3s. So I better not multiply by any 3 or else you're dead. Like the way we do this is you count how many rotations I can make. If you ever have something that you rotate and it's got like 3 or 9 or whatever, you're dead. So now what you're getting at is, do I pick the middle ones or not? Well, it's interesting. Let's dive a little bit deeper. Like over here, if I picked 1 from the middle one, then I got a 3. I'm dead. But you see this guy? I picked all 3. I'm not dead. So let's be...
You can't pick 1.
You can't pick 1 from there. Okay, that's true. Can people help to drive this further? So this is great. Nancy.
You want to either keep as many wheels full or empty as possible.
Aha, I heard the key words. Full or empty is the key words. The moment you have a not full, you know what happens? It just starts to be able to spin. The beautiful thing about this is that the moment you can start to spin, the number of ways to make it, the number of things is actually always going to be a factor of the size of the wheel. That's why in the 9 wheel, there's either one way, it's called grab the whole thing or grab nothing, or there's 3 ways, that's like what you saw here, that triangle, or it's 9 ways if you just pick something else that doesn't have any symmetries, if it doesn't stop, like repeat earlier. All right? So what you just got on is the only things that are not 0 mod 3 are the all or nothings. Did that make sense to people? The all or nothings means that in every single one of my wheels, I either picked everything or I picked nothing. That's the key point here. So all these lumps will be 0 mod 3, except for the all or nothing lumps. Let me write that down. So in this 17 choose 7, most lumps are congruent to 0 mod 3, except for some mysterious lumps. The ones which, if I have the, I'll draw a circle now, okay? I'm just going to call it a circle of 9, a circle of 3, a circle of 3, a circle of 1, and a circle of 1. And what you're going to say here is like, can someone give me an example of how I might get an all or nothing? How might I get like everything to be all or nothing? Give me one example. Okay, I already typed 3, 3, 1. So one way I could do it is if I took none, all, and none. Does that make sense? Like that's one way. That gets you 7 things. Remember, I need to pick 7 things. Okay, in that case, how big is this lump? Let's make a lump. This lump. What is its size? How many other things are in this lump? Well, nothing else. It's just got size 1. Size equals 1. Okay, now, what does that mean? I'm trying to figure out how many of these pictures are there altogether, modulo 3. I just found out that most of the lumps don't matter because they give me 0 mod 3. And all of these other weirdo lumps, they give me exactly 1. This is insanely cool. Okay, so this is insanely cool. Something neat is happening here, okay? So what we're finding out is that 17 choose 7 mod 3 is the same as the number of ways to pick all or none from 9, 3, 3, 1, and 1. Pick 7 things. Pick 7 things, all or none, from 9, 3, 3, 1, 1. Because each of those ways gives me one thing. It's a lump of size 1. So each of those ways, each gives a lump of size 1. Okay, so now I just have to know. How could I do that? Well, so far, how do you make 7 out of 9, 3, 3, 1, and 1? Well, remember we did something with base 3 also, right? We know that 7 in base 3 is 0, 2, 1 in base 3. What does the base 3 representation even mean? Base 3 representation is telling you how many ways? Yes, and like 3, 3, yes, x3, 3, x1 is the second way. That is correct. But what I want to say is like, how do you make, what does this 0, 2, 1 mean anyway? Actually, what this means is that the unique way to make 7 using less than or equal to 2 of less than or equal to 2 of each of 9s, 3s, and 1s is 2 times 3 plus, so 0 times 9 plus 2 times 3 plus 1 times 1. The only way that you can make 7 is with grabbing 2 3s and grabbing 1 1. That's what base 3 means. In base, like that's why base representation is nice. You don't have to be like there's two different ways to write the number in base 3. There's only one way to write the number in base 3, and you build numbers in base 3 from picking up like up to 2 of the things from each of the powers of 3. So here's the punchline. Here's why it works. Okay, what's this number of ways? Well, here's what I've got. I have 9s, 3s, and 1s. Okay, 9s, 3s, and 1s. I have some number of supply. How many 9s do I have? 1 9. How many 3s do I have? 2 3s. How many 1s do I have? 2 1s. That's because that's 1, 2, 2 in base 3 is 17. That's my supply of 9s, 3s, and 1s. And how many do I need to pick? I need to pick how many of the 9s? Well, I'm not supposed to pick any of the 9s because I need to go and make 7, right? The only way to make 7 is with like 3, 3, and 1. I have to pick 2 of the 3s and 1 of the 1s. Okay, so this is my supply, right? I've got 1 of 9. I've got 1 9. I've got 2 3s. I've got 2 1s. And I'm supposed to pick 0 of the 9s and pick 2 of the 3s and pick 1 of the 1s. What's going on? Jack Liu, did you want to ask a question or say something?
I was going to make a similar point about like the supply of 9s and 3s and 1s because that's a supply and we're picking from. That's a choose.
That's a choose. That's why it works. Bam. We're done. That's the proof. Because it's like I have to pick that many from the supply. Okay, so we are over time, but I want to say this is the heart of why this thing works. Now, I know we're over time, but I want to let you guys know a bit of like what was important in this proof. So there is an important detail of how I chose to lay out my numbers, because the reason why we intentionally wrote with only 1 9 and only 2 3s and only 2 1s, the reason we did this is so that the amount of supply would never give us like 5 3s to play with. Because there's another way to go and make 17. There's another way to make 17 dots. Actually, I could have like 5 wheels of 3 and 2 wheels of 1. If I did that, if I had 5 wheels of 3, then over here it might be a little bit wacky. Because it's like, well, suddenly I have more 3s than I can play with. Oh, that's a bad example. Better example would be just like, suppose I did 9, 3, and like 5 wheels of 1. That's a better example. I could make 17 dots with a wheel of 9, a wheel of 3, and 5 wheels of 1. Then suddenly over here I get confused because it's like I've got a bunch of ways to make 7 now. I could grab all 5 of those 1s. No, I could grab 4 of those 1s and a 3 or something like that. Does that make sense? The uniqueness breaks down. There's something here about the only way to make the 7, you were forced to grab both of those and only one of those. But if I had more choices, then there might be different ways to write that number 7 in terms of picking up different numbers of this batch. So that was one piece. And the second piece, just to drive home, is why is it important that it's prime? Well, if you go back here, remember I made some comment about how the size of the wheel is always going to be a factor of, the number of rotations will be a factor of the size of the wheel. If you were doing this modulo 10 and you have a wheel which has 10 things, it's actually possible to make a wheel so that it only has 2 rotations. Just pick every other thing. Now suddenly, that's not a multiple of 10. Do you know what I mean? Like if I have a wheel of 10 things, I might only pick up a 2. This whole proof requires that if the lump is not alone, then the lump is 0 modulo the prime. If the lump can be all kinds of weirdo things modulo the prime, everything breaks down. So that's why this works out. Okay, so that's it for today. That's this really cool theorem. I think this is a nice grand finale to finish all of this like counting and binomial coefficients and stuff on. And I guess I'll see you on Friday. I'll put the exam up right when the class starts on Friday, and the instructions were what I had sent before. If you have any questions, feel free to ask me. But see you guys.
Thank you.
Yeah, you bet.